You ready, Chris?
Let's do it.
Do it. Awesome. Good morning, good afternoon, and good evening. Thank you all for joining us for our latency webinar with the co-founder and CTO of Blocknative, Chris Miesl. My name is Laurence, and I am a product marketer at Blocknative. Welcome, Chris.
Hello.
So a little bit about Chris. Chris is an expert on latency. In his past, he worked at NASA, where he was involved in deep space probes dealing with real-time data. Throughout his career, he's worked with real-time data for ad tech, Spotify, and Apple, to name a few. Today, Chris is focused on real-time data in the blockchain ecosystem. So specifically at Blocknative, our real-time infrastructure enables validators and searchers to optimize staking rewards and trading profit. And Blocknative is a leading Ethereum block builder and relay provider. Like I said earlier, throughout Chris's presentation, feel free to add any questions to the Q&A section. And if we have time, we'll answer them at the end. So without further ado, Chris, let's hop in.
Great. Thank you, Laurence. Appreciate that. I thought I would start with a little bit of a story because Laurence kind of gave you a little bit of my background, which started in working for NASA. And what was latency like when I was doing that work on deep space probes? Basically, at that time, you have these probes that are out in Venus or Mars or farther out, and there's a certain amount of delay for the signal to get back to the Earth and to be able to process. And that might be a few minutes, it might be a few hours. So that's a pretty large amount of latency. But the actual latency that we experienced at the time was more like a day, because you get the signal back and then you have to interpret it. And so there's this sort of computational element, human computational element, to figure out what to do next in order to send signals to that spacecraft on any kind of adjustments or corrections or whatnot. So that was sort of my introduction to latency, and obviously it's a pretty large latency there. And then moving forward in my career, eventually I got to the point where I was building ad tech solutions. And in ad tech, you're dealing with billions of events coming in a day. These are basically page views, and then you need to make decisions on those and deliver a bid in order to capture that page view with the ad that you want to deliver. So you end up with complex bidding models, but they are all based on getting the data fast enough so that you have as much time as possible to make a decision within the window in which that auction is going to close. And so now we're talking about latency that is on the order, that's measured on the order of hundreds or even tens of milliseconds. And that kind of brings us to today with blockchain. And often people think that with blockchain, well, why do we really have to worry about latency? I mean, these blocks take a little while to make. If you're on Ethereum, post-merge, it's a 12-second cycle where we build these blocks. So that doesn't seem like a lot of latency. But as we will see, it matters. So why does latency matter so much? And the reason is it's not a technical reason. It is a very simple reason, which is it's an information advantage to know about something sooner than someone else. And if there is money involved, then that means there's a trade advantage. And that trade advantage will then give the holder of that advantage more time or get in front of other trades in order to generate more money. So latency very directly correlates to more money, basically. So that's why there's a lot of attention in this area, and there's a lot of effort in order to reduce latency, which leads to whenever you're talking about latency, then you're talking about serious infrastructure. Because in order to provide these kinds of low latency solutions, you need to do a lot of infrastructure, not just to make it resilient, but also to make sure that everything is as fast as possible. Think of it like your pipes need to be as clean as possible so that everything can flow through as quickly as possible. And so you have large infrastructure companies that do sort of custom deals with ISPs and other network infrastructure players to basically optimize the pathways to go faster than sort of normal internet traffic. And that's sort of why when we talk about latency, infrastructure matters. It matters hugely. So let's bring this home now to what's happening today. And we're going to be focusing obviously on the Ethereum. Let's talk about the transaction and as a consequence, the MEV pipeline that we experience today. So just a quick review. a user has some kind of intent that they then sign through a wallet, and that wallet then sends that transaction through some service provider to a mempool. That mempool propagates around the world. Searchers then see those transactions in the mempool and do action on those to make decisions, and then send those reactions to the initial trade or the initial transaction to a builder. So that would be, for example, that's sending a bundle that may contain a front run or a back run or a sandwich. And then those builders send the blocks that they build to a relay, and the relay then sends the blocks that it receives, makes them available to validators via MEV Boost, so that when the validator is ready, somewhere in that slot to propose the next block, then that information is available to them so they can do the proposal. For our discussion, we're going to focus on the sort of the signed transaction part of this. So that's where the user intent has already been expressed, the wallet has signed it and has sent it to the mempool. We're not going to go earlier than that. And then, and we're also not going to focus so much on what the validator does, but more that we just get it to the validator. So this is sort of the, from signed transaction receipt in the mempool all the way through block delivery to the validator is kind of where we're concerned. And the kind of latency that we're going to be talking about, I kind of divide into two main categories. There's compute latency and there's transport latency. And to go back to the example that I gave from earlier in my career, you know, the transport latency is sort of the light time from the spacecraft down to an Earth receiving station, and then from the Earth receiving station to wherever the computers are and the people are. In my case, it was JPL to actually process that information. And then the compute latency is going to be decoding and other kinds of computation on that, plus whatever kind of human computation is required in order to make a decision. Oops, I skipped ahead there. And so those are the two classes of latency that we're going to discuss. Now, I'm going to now work through those different elements of the flow of transactions, and we'll talk about the latency inherent in each of those and how we can respond to those. So the first step is is the mempool. And just as a quick reminder, there is no the mempool. There is, everybody has their own mempools, and there's a P2P network that tries to keep them sort of synchronized, but this is, after all, a decentralized world. And there's sort of, time it takes to go from one mempool to another, and it's like a big mesh. And so there's a lot of delays in there. And so the kinds of latencies that we experience then in a mempool is that how close or far away are the peers to the current mempool that you are operating. What is the quality of the network links? So they stay up? Do they go down? Is it dial-up? Is it fiber? What is it? And then these peers are changing all the time. So peers appear and then disappear, and the node, the Geth node or the Nethermind node or what have you, is constantly updating its peering table, and peers are leaving and peers are arriving, and there's a certain amount of time it takes to accept a new peer and verify that the link is good, and so that creates some latency, and that kind of speaks to the liveliness of those peers. And the less lively the peers are, then the more churn there is within a particular mempool to be able to find more peers. And then in order to get into the mempool, it's actually quite a lot of compute that has to happen. So there is a sort of a validation pipeline inside of a Geth node or another Nethermind node or whichever node you're using to verify that the transaction that is being received is in fact appropriate to put into the mempool. So you have to kind of dedupe it. You have all these peers. A typical Geth setup will have 50 peers, and so you might be getting the same transaction from each of them, and you only want to take the first one. And then once you receive that, you have to verify, is it formatted correctly, and then and then validate whether it is an acceptable transaction. So for example, you check that the from address has enough funds in it in order to properly fund the gas expectation for that transaction. Well, how do you actually do that? you then have to look up the funds for that from address, and that might require a lookup in the database, in the chain itself. And those lookups can be rather expensive. If you're running get, for example, the chain is stored in its fully Merkleized format, which means that you're doing a lot of disk hops in order to find the data that you want. So that can be a little bit slow. And then and that sort of speaks to this sort of having to find the chain state in order to properly validate transactions that rely on that chain state. And they all do from the from address, and depending on the complexity of the transaction, there may be other chain states that need to be sort of qualified to make sure that they're okay. So how do we respond to all of these sort of challenges for latency? Well, one of them is you do a lot of shortcuts on the validation if you want to kind of tune that. And there's all kinds of tricks that you can do there to reduce the time it takes to do all of that validation. Maybe there's some sort of caching that you do to have some of that chain state in memory, so that you don't have to go to disk. You could have larger sections of the entire chain just basically mapped into memory so that you can get to it fast. There's all kinds of sort of techniques used in order to get through that validation pipeline faster than stock Geth or Nethermind might do. And there's even some newer, there's some other clients like Aragon, for example, that has a fundamentally different storage format under the hood, so that it doesn't have to, so these lookups don't have to be as inefficient. They don't need to do as many disk reads, and that makes them faster for the validation. Another way on the transport side is to use a private network to get access to pending transactions faster than you might just waiting over the peer-to-peer network. And the BDN from BloxRouter is an example of that. That's very popular among traders and other infrastructure operators in this space. And another option might be to sort of optimize the peering algorithm that's used in these node clients. A well-known one, there was actually a paper put out a few years ago for a design called Perigee, which changed the peering algorithm so that it optimizes for low latency peers, as opposed to the stability of those peers or the sort of randomizing the peers. Randomizing the peers is actually good if you want to have a really healthy network, but it's not so good for latency. So Perigee focused on the latency issue, but it was sort of realized that in a network topology, when you do that sort of a game where you optimize for latency, it's very easy to have network segmentation, which in the crypto world we tend to call eclipses, as in eclipse attacks, where a part of the network is sort of isolated from the rest of the network. And so that was sort of abandoned as not such a good idea. There was another product called Peri, modification to Geth in this case, which basically applies that for a few nodes, and that is advantageous to those nodes. But as long as that's not deployed very extensively in the network, then it doesn't cause some of the network problems. But it can give a few nodes a specific advantage. So those are kind of some of the responses that teams have done in order to make mempools more efficient and current, especially if you're, let's say, a searcher. All right, speaking of searchers, we'll move on to that next one. Now, going from the mempool to the searcher, now you have more compute latency because the searcher has to actually parse the transaction and then filter it to figure out, is this an opportunity for that searcher to be able to capture some MEV? And then once you've set up your capture, whether it's a front or back run or a sandwich, then you need to simulate that to make sure that the outcome is as expected, and you're not going to basically send a bundle that is going to lose you money. And you might also want to simulate it under a condition where if the inputs to that aren't what you expect, that it fails very rapidly, so you don't waste a bunch of gas. And then the searcher also has, of course, the standard transport latency, getting from the mempool to the searcher, and then sending those bundles on to the builder and dealing with the rate limits that most builders will enforce. Builders will have rate limits in order to prevent too much spam or low value bundles from a searcher, because there's a compute cost to them since they're validating. And typically what builders do is they create multiple tiers and there might be a fast tier and a slow tier. And depending upon your success rate, the quality of your bundles, then you sort of get elevated to the fast tier versus the slow tier. And that way a builder can kind of manage their resources in order to get the best possible blocks without being, wasting too much time on low value inputs. So some of the responses that searchers have to this. Well, we'll start with proprietary compute environments, which is my euphemism for what is typically called in the classification of alpha. This is searchers doing magical things under the hood that they're not going to tell anybody about in order to compute the bundles faster than other people. There are numerous techniques for that. We're not going to get into those. So the other opportunities are that they can, a searcher can time their bundles so that against the slot periods, the blocks are typically prepared so that they can be proposed at the beginning of the slot or the end of the previous slot, depending on your point of view. And most validators are going to wait close to that edge in order to have the most valuable blocks. And a searcher is sort of incented to kind of be careful about their bundle timing, because you want to put all of your compute, all of your sort of capacity into that partial period of the slot where you can have the most, you can provide the most value and have the most likelihood of being successful. And then another one is to minimize the transport latency to the builder by co-locating with the builder. So let's say if the builder is operating out of an AWS region, then determine where that region is, and then make sure that you're searching in the same region, or even have a conversation with the builder and see if you can do a direct connect link to even further reduce the latency connection. It reduces the number of switches and routers you go through in order to get to that builder, which can be quite material. So speaking of the builder now, moving through this pipeline, the builder, of course, now has to validate every bundle coming in. Has to make sure that it is in fact a valid bundle, that the value that is expressed via is in fact correct, and then it might have to do some filtering potentially, depending on which jurisdiction it's in. It might have to do filtering based on jurisdictional requirements. Like in the United States, we have a list of addresses that the government would prefer not to transmit. So if you're operating a builder that adheres to that, then you would have to put in those filters. And of course, that takes compute time, which slows everything down. And then you have to do calculations as a builder on prioritization of the bundles. I talked about like fast lanes and slow lanes to sort of figure that out. And then of course, once you've built the actual block, then you need to simulate that, or in the process of building it, you're simulating all of these combinations to make sure that the block that you finally produce is in fact a valid block. And on the transport side, obviously the connection between the searcher and the builder is going to introduce some transport latency there. And then you have to send it on to the relay, which has some transport latency there. And then the relay itself may have some limits. Different relays have different limitations. Some don't have a limit at all. And so you have to sort of respect that. Otherwise, you're going to end up just sort of being in the wrong, at the wrong tier with that relay, because they will treat you potentially as spam. So you have to sort of respect that. And you have to do that slightly carefully, right? You don't want to just rate limit your building. You want to actually, do everything as fast as you can, but always try to reserve, make sure that you handle that rate limit in a way where the best block always does get through. So it's there's a little bit of nuance there. So the responses to that, again, there's the proprietary compute improvements that you can do. So every builder has done all kinds of clever things to their build environment in order to be more efficient. It's sort of very similar to what the searcher does, but they're just doing it sort of on a larger scale. Builders will typically be running much beefier hardware in order to have a fast compute capability, and they will also make sure that within their little ecosystem, if they're using external services, that they have very high-speed links. Builders also look at block timing, again, for the same reason I said before, which is that you might, it's sort of more productive to be building faster and better towards the end of or near the beginning of the next slot. And that'll give you more success as a builder to have the highest possible bid. And of course, you would co-locate, that's actually incorrect. You would co-locate with the relay. I'll correct that afterwards. But the builder would want to co-locate with the relay to sort of reduce that connection time. Right, that takes us to the relay. So this is pretty much the last one in the list here. And the relay, what does it have to do? It has to like verify the signatures, it has to verify the fee recipient, it has to simulate the block to make sure that it's valid, that the bid is the actual value that would go to the validator is in fact the bid, so that it's an honest submission, and it might have the same or different filters as I discussed before based on any kind of regulatory constraints. And it has to do all of these things in order to make sure that the block that is delivered to the validator, it sort of meets all of the conditions and is perfectly valid. There have been some new innovations here on the relay space to do optimistic simulation. So in the case of bid validation, for example, or validating the block itself, then by doing an optimistic, you can do that asynchronously, so it doesn't slow down getting the block to the validator. But then there's some kind of sort of bonding mechanism so that if the builder, in fact, did fail in creating a correct block, then there's some sort of economic mechanism to force that builder to sort of make right with the validator, since they essentially delivered a bad block that the validator was not able to put on chain, or did put on chain, but the promise via the bid was not achieved in the actual value that was generated. So, and several of the relays are moving in that direction. And then, of course, the usual transport latency issues of getting the blocks from the builder and sending the blocks to the validators, and sending the blocks to the validators in the transport side for relays is a little bit interesting, because the relay is basically fanning out to the entire universe of validators, 500,000 validators around the world. And so they're all in different locations. So that's why relays have to do a lot of infrastructure to make sure that they can provide low latency to validators wherever they are in the world, whether they are in Asia or whether they're in Europe or in the US or in Africa or what have you. The latency needs to be low no matter what. And that requires sort of configuring things in the right way in order to achieve that, because validators do try to get to the edge to get the best possible block, and there are some pretty strict constraints on how fast the relay has to respond to that. So the responses are maybe not proprietary compute, but definitely a proprietary network, and with distributed edges, where you basically do a lot of sort of edge computing techniques in order to get close to where all the validators are, which means that relays will have points of presence all over the world in order to have good coverage based on where the validators are. Another way to approach this would be to just do full-on distributed relays, so that you're basically running multiple relays in different parts of the world to service those regions of the world. And then having some kind of proprietary network under the hood that tries to keep those synchronized as much as possible. Obviously, you would want to co-locate with builders or have builders co-locate with you. And then potentially you would co-locate with validator pools. So if there are certain validators, let's say Lido, for example, that has a huge footprint, then if you know where those validators are operating out of, then maybe you want to have the relay have a point of presence that's very, very close to that, like co-located with that. And that would be advantaged. That would be an advantage to that validator pool, because they're going to get incrementally better blocks, because they don't have to worry about the transport side as much. So that gets us through the whole pipeline. I know that might seem a little bit of exhausting, but part of the message there is that there's just a lot of steps. There's just a lot of places where there's all kinds of optimizations that can be done, and to sort of improve latency, and therefore to improve the value of those blocks, and the value that is ultimately in our current setup that is ultimately sort of captured by the by these actors that are involved, the validator getting the best possible block value, searchers getting the highest win rate on their blocks and things like that. So I wanted to briefly sort of switch to, how does this sort of translate to traditional finance? And also give me a chance to put some color on the slide with Michael Lewis's book on flashpoints, which I would highly recommend reading it. It's actually a very entertaining view of how high frequency trading works. And what the problems that they express there are basically the fundamental latency problems of that I said at the very beginning, which is if you know some piece of information earlier than someone else does and you can act on it, then that's going to translate into dollars. And that's what a lot of these high frequency traders basically did. And they realized that if they had super fast links and if they could co-locate with the exchanges, so there's like a dozen traditional finance exchanges, then they would have a big advantage in sort of being able to arbitrage between a single trade distributing out to all of these exchanges. So that trade goes to exchange A and exchange B, and you have a faster link between A and B versus what the normal trading outfit can do. And therefore, when you see that trade coming in, then as one happens on one exchange, that creates an imbalance between the exchanges, and that allows you to arbitrage that. And HFT outfits basically were setting up racks of high-speed computers in the basement of the exchanges or in the building adjacent to it, and to do just that. And that became quite a good monetization technique for the exchanges themselves. So exchange would set up and then basically buy the building next to it and rent out that space to HFT traders and say, hey, if you want to get ahead of things, we'll give you some rack space right here. So it became its own little industry. And then, of course, you can do fancy compute like FPGAs to make it even faster than normal CPUs. And the response to that was there wasn't a lot of response to that. There was some social pressure. So part of the main story of Flashbots is the story of the IEX exchange. I think it stands for Investor Exchange, which traders can opt into, and it does a trick where it knows the latency to every other exchange, the physical latency to every other exchange over the wire, and it would delay sending the trade to each exchange based on that latency, and basically optimize for every other exchange to receive that trade at the exact same moment. And of course, they didn't allow any HFT traders on-prem with when they received the trade, and it's very successful. It achieves the goal, but it's less than 3% of all trades go through that platform, so it's not really that material. And of course, there have been regulatory changes. So in the United States, the U.S. government has made some changes in order to have a regulatory pressure on some of these techniques that are used by HFT, but they only work in HFT can move much faster than Congress in the U.S. can adopt rules. So in the end, if you from what I described, you can see that even in TradFi, infrastructure matters. It's all about the infrastructure. It's all about the pipes. It's about networking and high-speed compute and sort of optimized compute. So how does this sort of affect the activity that searchers and builders and relays do today? What is going to be sort of the consequence of this? What is sort of the natural direction that this might go in? And I think what we can expect to see, and we're already seeing some of this, is a consolidation between searchers and builders. That they're going to co-locate, or they're just skip that part and just become one. So you have searcher builders, and so these are builders that are also doing searching. And there's huge advantages to that. They might accept other bundles from external searchers as well, but then they do their own searching on top of that that they can then do with pretty much no latency at all, because it's in the same it's in the same compute environment as the building that the block building that happens. And then the other expectation would be that there'll be a centralization of builder connectivity to validators via relays or maybe even direct through proprietary networks. And I think we're starting to see that now, that more and more the builders want to be on a high-speed network. The validators, especially pools, can be on a high-speed network, and the relay is going to be on a high-speed network, and everybody's sort of working together. And the number of high-speed networks is much smaller than the number of builders and validators. So there's sort of centralization there. So where does this lead? Does this in fact lead to MEV dystopia, which was described by the Flashbots team almost a year ago in Amsterdam? Like, how do we avoid this sort of complete vertical integration where you have a large validator pool that basically runs its own set of builders and its own set of searching, and and insofar as they can be successful at that, then they have a sort of an API advantage on their, revenue generating advantage on their stake, and they could then plow that advantage back into their stake, increase their validator pool set, and you have sort of a flywheel effect. And the next thing you know, you have this sort of dystopia where the entire network is no longer centralized anymore, decentralized anymore. It's completely centralized at that point. So is it inevitable? And I would argue that it is not. And the reasons why is that searching is an incredibly dynamic activity. There are new protocols that are appearing all the time, new opportunities, new techniques. And the builders can differentiate on all kinds of different block space offerings. It's not just MEV, but there are other things that are going to become more and more valuable, especially as we layer on L2s and other compute concepts on top of the core Ethereum platform like EigenLayer. Then there's the value that the builder has is how they optimize the use of that block space, and that's going to, there's going to be a lot of innovation there that I think is going to allow new entrants and smaller actors that can move very quickly to be able to be quite competitive. And then on the relay side, I think, keep in mind that relays is sort of a temporary thing until we have in protocol PBS or enshrined PBS, ePBS. And but in the meantime, I think it's very possible that different validator pools are going to have different validator preferences, and that's going to create the need for multiple relays to service that. We see that today, as far as there's some of the relays serve do not censor any transactions, and some relays ensure some kind of sort of compliance with particular regulatory requirements in certain jurisdictions. And there's a demand for both of those. So that's great. And so that kind of brings us to today. And one thing that I wanted to add is that a lot of these ideas were proven or became sort of front of mind over last week. So some of you may know that there was an interesting event where a validator was able to extract a very large amount of funds by basically sort of front or sandwiching essentially a searcher or a group of searchers. And they did that because they had visibility into the block, even though the block was not being propagated, and they could then swap that block out because they were the official proposer at the time. They could swap that block out with a block of their own making. And because they had visibility into the searcher, and they had carefully constructed a bait for those searchers in order to get them to kind of max out their attempt to get profit or max their leverage, they were then able to pull all of that away from the searchers and capture it for themselves. And that was actually caused by or enabled by a vulnerability in relays that was very rapidly addressed. But there, it sort of illustrates that there is an opportunity there for sort of latency-based games, where if a validator wanted to sort of do a switcheroo on the block after they have signed it, and they happen to be able to propagate that faster on the network than the relay can, then they might have an advantage. And so there's a lot of talk now in the relay community, of course, about how to mitigate that, because it's sort of an interesting, basically a race condition vulnerability to how the network operates. So, but that is like an example of exactly what we've been talking about in this presentation, and it's very sort of real world. So, and that yeah, so that kind of concludes. If you want to, I'm happy to continue this conversation with anyone on our Discord. There's a QR link for that if anybody wants to check it out. And otherwise, it's been a pleasure speaking to you today, and thank you very much.
Thanks, Chris. That was so wonderful and insightful, and I always learn something when I hear you speak. And I think it's like super interesting to hear about all the similarities and differences in these latency wars between the ecosystems, and also all of the specifics of each layer of the pre-chain and how each one has things that they can improve latency. So really cool. And thank you for sharing that knowledge. We did get some questions. If you haven't asked your question yet, please throw it in there and we'll answer them. We have 2 questions from the Q&A. Johnny, the Discord QR code, Chris, can you go back one so that people can grab that Discord QR code, please? Perfect. We'll leave that up so you guys can scan it. So we'll start with these 2 questions that are here. First question, Chris, is has standardized block timing post-merge had any impact on infrastructure demands or needs?
Yes, it has. So there's sort of a whole new level of interest in latency post-merge because of these fixed block times. Because before you could play the latency game, but you had to kind of play it all the time because you didn't know whether the block is going to happen in the next second or the next 50 seconds. So you kind of have to make some assumptions there, and they're a little bit difficult to make. So by transitioning to a sort of a 12-second clock, if you will, then now everybody knows that everybody that is in this, that is building blocks and relaying blocks knows that, in the first 6 seconds, any blocks that you built, they're kind of, they're cute. But it's only in the 7, 8, 9 second regime where things start to get really spicy, really interesting, and the real competition happens. And so the infrastructure providers for this, whether it's relays or builders, that's where they sort of invest their energy, is to make sure that they are sort of optimized for that period where all the action is happening. And that action can actually bleed into the next slot a bit. There's been some research that shows that you can kind of delay into the next block a little bit farther than I think people originally expected. Like we see it almost like a second or two sometimes, and still be able to get propagation going well enough to get the attestations necessary so that you have a successful on-chain block. So it's definitely, it's sort of compressed everything, and everybody knows the period of time when everything needs to happen. Well, before we didn't, it was sort of smeared out over maybe a minute, averaging, at the time, like 13 and a half seconds, but it was kind of smeared out. So it was a harder problem to solve in that regard. But now it's a harder problem to solve in terms of everything is focused in one little area and you know exactly when it is. So yes, it has changed infrastructure requirements. I think it's actually, speaking from the point of view of Blocknative, we have scaled up in order to support that narrow window, and we don't sort of worry about the other periods quite as much. So it's just a different way to organize the infrastructure.
Next question is, are there any current decentralized techniques for searcher builder co-location?
Good question. And I think part of, it's part of the thinking behind some of the in protocol PBS conversation is how do we do that? I think that right now there's no sort of strongly established protocols for doing that. So right now it's sort of going down the sort of standard co-location kind of route. And when I say co-location there, it's not so much that I'm not seeing that many searchers that are actually trying to co-locate with the builder. It's more the builder basically taking on more sort of searcher behavior. And so the builder already has to have a pretty significant sort of infrastructure commitment and spend And so that kind of puts them in a place where they're willing to spend on the searcher side, and maybe even put capital into searcher techniques that require capital, right? So they're less about atomic bundles, but other kinds of searching that require a capital commitment. So several of the major builders are, they're traders themselves, and so they can, in addition to reacting to what is in the public mempool, like a typical atomic searcher would do, they can also do sort of interesting long tail searching or long tail MEV that is based on sort of analytics about the behavior of price movements over time. They can do centralized exchange to DEX trades, because they have the capital to be able to deploy on centralized exchange to do that. So I think that searcher builder co-location is becoming more about builders assuming searcher roles, as opposed to searchers trying to actually physically be near builders. But I'm not aware of any sort of viable decentralizing protocols for searchers. In fact, what searchers are doing, they're basically just they ramp up how fast they send bundles, and they send this. We see a tremendous amount of duplicate bundles being sent. Searchers are basically just trying to game whatever it is that the builder is doing. A classic technique of a builder is that to prioritize searchers is that they put them in, there's sort of the fast and the slow lane, and the fast lane, is based on some kind of analysis of the success of that. Like, for example, the Flashbots builder does this, or at least the open source version. And so there's some kind of like reputation system based there. And so searchers, for example, will keep changing their keys in order to appear as a new searcher and to try to defeat these mechanisms and get into the fast queue. So most of the searcher activity is to figure out how to optimize themselves for the builder, as opposed to sort of develop a decentralized protocol for searchers to connect to builders.
Amazing. I'm loving these questions. They keep coming in. How will PBS impact ZK L2s? Since L2s are run by centralized sequencers, does this have any role there at all?
So the PBS work that's happening is pretty predominantly in the L1 layer. The question of how does this affect L2s? They're all centralized. I mean, I think this is a long-standing not just question but debate, and there are numerous L2s, starting with Optimism, that are working hard towards coming up with a way of doing a decentralized sequencer in order to sort of get around the sort of high trust that you have with a centralized sequencer. But hopefully at some time soon, maybe even this year, we'll see some results there. But in essence, they're kind of, if they decentralize the sequencer, then they're kind of going down the same road that we already built with Ethereum, and they kind of have the same trade-offs. So it'll be interesting to see what what solutions they can come up with there. But I would say that the bulk of the PBS discussion right now is at the L1 layer, and not so much. But I would say that the L2s are definitely considering and watching this space, and trying to figure out how they can operate in a sufficiently trustless environment. Right now, with the centralized sequencers, there's a tremendous amount of trust that they are not going to do their own MEV extraction on that. And you could even argue that maybe they should do their MEV extraction there, as long as it is benign to the transaction originator, and that can be sort of monetization technique for their protocol. So, I mean, I think there's sort of arguments for that as well. But to answer your question directly, the PBS discussion is primarily just on the L1 layer at this point. I think we have to solve it there, or be able to demonstrate progress towards a solution there before we can really think about how it would work on an L2. Otherwise, the L2 is just sort of repeating the same things that we're doing on the L1.
And for anyone who doesn't know what PBS is, that is proposer builder separation, and that would be in protocol.
Yes. Yeah. So
which is being done with MEV Boost right now, but
yeah. And there's the term that's being used more and more often now is ePBS. So that's a small e and a large PB and S. And the that stands for enshrined PBS. So enshrined in the protocol, if you will. And that means that it's sort of baked in. And at that point, you do not need, it removes one class of actor in this pipeline that I've described today, which is the relay, because the relay occurs over the P2P network through the protocol directly instead of requiring an additional actor to be able to provide that service.
If you have more questions on that, feel free to jump in our Discord. We have a lot of resources we can help you with. Okay, next question. What is the incentive of relays? How can they break even with the cost of building low latency relays? Currently, most of the builders and searchers seem to pass through the profits to proposers. Will this affect the latency arms race?
Excellent question. I mean, this is something that we at Blocknative think about a lot. I think about a lot because we operate a relay. And all the relays that are operating in the world today, there's over half a dozen relays, or half a dozen entities operating relays, some of them operating more than one relay. They're all doing it sort of for public good. And there's sort of no direct sort of monetization conversation that's really happened. If you're interested in this topic, I would definitely recommend a recent podcast of the Bell Curve with our CEO, Matt Cutler, having a debate with Hasu on this very topic that aired on Tuesday. And we can drop the link somewhere to make that available. But it's sort of an interesting conversation about sort of relay economics. And I think it's a tough question. I think it's important for the relays to have some kind of economic incentive to sort of cover the quite substantial costs of running a relay. And it's not just the costs of running a relay, but it's also the responsibility of running a relay, right? So if a relay has an issue that then causes a validator to miss a slot, then the validator can get rather upset with the relay and say, "Hey, I missed this slot, and because you didn't do the thing that you were supposed to do," and that slot might have been worth, half an ETH of block value. Beyond their proposer reward. And, that's pretty substantial money. And if you're a very small validator, then you might only win a block every couple of months, might be every 4 months if you're a single validator, or a few weeks if you run a few validators, if you stake more than 32 ETH. And so missing one is actually super material. It could make or break your year in terms of covering the costs of running that validator. And then if you're a pool, then if there's enough of these sort of missed slots, then you're not going to be very happy with that relay. And there's been a lot of conversation about whether relays assume sort of a monetary responsibility to the validator when those issues occur. This is very relevant right as we speak, because right now, post the Chapella fork that happened yesterday, there are some challenges. One of the consensus clients is having some issues and how it interacts with MEV Boost. And this is causing sort of a higher missed slot rate. All of the relays are working together to try to understand this and working with that consensus client to try to sort of mitigate this issue and understand it. But depending on the validator, they might be rather upset about missing those slots and want some kind of sort of financial remuneration for that. And it's, do they go to the builder? They can't go to the searcher because they have no idea who that is. Do they go to the builder? Well, they're going to go to the person that they're interacting with, which is the relay. And so that creates a little bit of a tension there, if you will. I don't want to overplay. It's not like conflict, but there's a little bit of a tension between validators and the relay in terms of performing on delivering blocks. And then the relay is responsible for not only addressing that attention, but also having all the infrastructure or over provisioning to make sure that they can deliver those blocks. And of course, there's no revenue in there. So I think that the two sort of main paths for revenue conversation on relays is there a way to monetize relays? There's some pros and cons to that. Again, I would go to that podcast to hear out sort of an interesting debate on that. And then another way is to treat relays as a public good, a temporary public good, until we have ePBS, and then maybe the the Ethereum Foundation or other entities that are funding public goods in this space can help support the relay operators.
Awesome. We have many questions coming in. We'll have time for a couple more. One question came in: I'm new to MEV. What do you recommend to study? What books to read? Where could I find a team? I can go ahead and answer that. And Jules is our head of content. He'll drop in some links, but Matt, our CEO, actually gave a really great overview at ETH Denver that was recorded that you should definitely go check out. And Jules will put that link in there. We have a few other articles that are good on our blog. I don't know, Chris, if you have any other ones that you would recommend, if that's a good place to start.
Yeah, so a lot of this stuff is pretty new. And so there's no book. You just kind of have to keep up with what's sort of happening online about this. I think that definitely keep an eye on the Blocknative blog. The blog section. Go to blocknative.com/blog, and you will, we post pretty often on this topic. Flashbots obviously is a great source of information for that. You can go to the Flashbots forum sites, and there's a lot of conversations there. And then you'll also see a lot of information on the Ethereum Foundation forums about this. This is sort of a hot topic there. And, the Ethereum Foundation is very involved in this whole MEV conversation with relays and all that stuff because, in a sense, from their perspective, I think it's sort of, they're kind of seeing how this plays out because that also informs how ePBS gets deployed. And in fact, they're paying such close attention to it that they actually added a new item to their roadmap that now is the next most important item after the fork we just had. I'm not saying that there'll be a change in the next fork, but it's this sort of this scourge layer that they're talking about, which is to figure out additional mitigations that might be relatively straightforward that they could put in to the protocol without having to wait for the full enshrined PBS solution. So those are the, Blocknative, Flashbots, Ethereum Foundation, I think. And if you Google for MEV, you'll be overwhelmed. So, be careful. The other thing I would point out is that you try definitely, this is general for crypto, is to, concentrate on things that are relatively newer instead of older. Like the thinking on MEV 2 years ago, very different than the thinking that it is today.
It's an ever-evolving space, that is for sure. Okay, next question. Do you think shorter or longer block times are better for lowering the barrier to entry for searching?
I think that there's a bit of a trick question. I would say that if the block times are fixed, then it doesn't matter as much. Whether it's 2 seconds or whether it's 12 seconds, all the action happens in sort of the last quarter of whatever that slot time is. So I guess maybe it's not tricky. I guess the answer then would be that the longer block time can make it easier computationally for a searcher, and therefore it's easy to enter into that space. But then other actors can optimize for that, just like they would optimize for a 2 second slot time. So the competitiveness of that searcher, I think, is not necessarily that different. As an example, if you want to be on approximately a 2 second slot time, the equivalent of 2 second block time, like with Polygon, then obviously the work that you have to do as a searcher to be able to react needs to be more, pretty efficient. But you still have the same pressure that you would have with, let's say, Ethereum, where when it gets really interesting at that sort of sweet spot in the slot time, then large actors that are well financed can kind of kick in and do their thing. So.
Awesome. Okay, last question, because we are at time, actually over time. Thank you for doing this, Chris. This is a long one, but I like it. How important is private order flow for builders and relays? For instance, Flashbot Protect is only open to Flashbot builders who primarily use Flashbot's relays. We also verify empirically that relays win. Most plots tend to have more private order flow that we cannot observe in our MEV pool. Surprisingly, this effect is not quite strong for builders. Will the importance of private order flow lead to further vertical integration between relays and builders? Will this contribute to a slightly more centralization?
Yep, good, long question. And I may not get all the nuance of it, but I mean, at sort of at a high level, I left out in my presentation the sort of the what happens before it gets to the mempool, and that's the sort of private order flow area. So the latency game can be completely circumvented if you have information that no one has. It's no longer about whether you have information before the other person. You just have the information and the other person doesn't. And that's a sort of an insurmountable advantage. So the complete version of MEV dystopia is that it goes all the way to the intent layer of getting the transactions in the first place. And you have some kind of sort of not centralized, but vertically integrated relay builder and searcher that has massive proprietary order flow, and that'll be a huge advantage. So in general, if proprietary order flow is sort of outside of the latency equation, because the difference between one actor having that proprietary order flow and the other actor it may as well be infinite time, because the other person never sees it. And so I don't know if that's quite answering the question, but that's sort of the framework for private order flow, that it's not a latency thing at that. That's just it's like a black and white sort of, you have it, they don't, you know it, they don't, and you can print money from that. So yeah, and that, but I think there's a question there of like, how would you get that? What are you offering in exchange? Is that being done in a way that is actually favorable to the user that initiated the transaction? I think there's a lot of sort of interesting variables in there. There's sort of some interesting in that space. There's some interesting developments there. Like very recently, Gnosis announced the MEV blocker, which is basically an RPC endpoint that you would send your transactions, and then they actually operate an order flow auction, an OFA, that guarantees, I think, 90% of the backrun and backrun only MEV is returned back to the initiator of that transaction. And so if that is successful, for example, then that would represent a sort of substantial proprietary order flow being generated through that gets to searchers that are sort of bidding on that. That's going to force searchers to bid their margin down to near zero, because that's what they're competing against. And then the interesting thing about that is that it increases the trust level required of builders, because builders now are able to sort of tap into that proprietary order flow, and they have to make sure that they don't sort of misuse that information. It's sort of the same trust level that we currently have with relays. Now it's being pushed more and more to builders. It's already there a little bit, but it's definitely a stronger trust requirement of the builders to do that. So maybe that answered maybe some part of your question there.
You answered a bit of someone else's question as well, so that was perfect, Chris.
Okay.
2 birds with 1 stone. Amazing. So, okay.
Yeah, I was going to say, we posted our links in Discord and whatnot, and I'm happy to answer any other sort of questions, sort of asynchronously on Discord. And I've really sort of enjoyed this experience, and it was great to speak to everyone about the latency topic, which I have a certain sort of passion for.
Yeah, thank you so much, Chris. And that link is in there. We'll also be sending out a follow-up email with a recording of the presentation, and then all those links will be in there as well. So it'll be easy for you all to get that. So yeah, thank you all for being here. Thank you, Chris, again for that. And we'll see you all next time.
Thank you all. Bye-bye.